Bismillahirrahmanirrahim. Welcome to my channel Science and Engineering Knowledge Academy. I am Afnan Haider Khan. Today we are going to discuss conduction, the Fourier's law of heat transfer in this part 1 of the lecture 2. Now we know that conduction mode of heat transfer takes place in all three states of matter: liquid, solid and gases, and the heat transfer takes place due to the collision of the particles with each other from higher temperature region and transfer the energy to the lower temperature region. So, and for that it is important that there would be no bulk motion of the matter, because that is in the case of the convection only. In case of the conduction, there is no bulk motion, there is only collision between the particles, due to which the heat transfer takes place from higher temperature gradient towards the lower temperature gradient. In other words, we can say that the energy transfer from more energetic area to the less energetic area of the particles of a substance due to the physical interaction between them. And obviously for the physical interaction, we would definitely require a medium for the transfer of heat from higher temperature zone towards the lower temperature zone. Right? And this was the governing equation which we have actually shown in the last lecture, that this is the Fourier's law of conduction equation. Now, to get into the detail of this equation, let's consider this rod, which has a uniform cross-sectional area A, and it has a temperature T1, right? This surface has a temperature T1 and it's basically hot at a higher temperature. Similarly, the N2 over here, T2, it is at a lower temperature. So this is the lower temperature region, right? This surface is at lower temperature, this one is at higher temperature. Now, the temperature difference between these two, delta T, is given as T1 minus T2 is the temperature difference, and this rod is insulated from the lateral side, you can see over here. So it is insulated from the lateral side, and there is only one direction in which the heat can flow, and that is this x direction along the length, right, along this delta x. So now first what we see is that the more this temperature difference is, the more we would have the heat transfer rate. So the heat transfer rate would be directly proportional to the temperature difference. The more we have the temperature difference, the more heat transfer rate would be. So the heat transfer rate is directly proportional to the temperature difference between the two ends. Similarly, since this area is uniform throughout, but if we increase this area, so by increasing the area, right, what we are doing, that more particles have interaction with each other, right? So therefore the heat transfer would take place more quickly, because now more particles have interaction with more particles, neighboring particles, and that is why, due to this increase in the number of interacting particles, the heat transfer rate would increase, and that is why this Q of x is also directly proportional to the area, right? Now let's come towards this delta x, which is the length of this particular rod. Now this delta x, the more you increase this length, the more you increase the distance between these two ends. So what would happen? The heat transfer rate would reduce, because it will have to cover a long distance, right? So it is inversely proportional to this distance or the length of the rod. Now let's combine all these three equations and we will get this relation. Q of x is proportional to A into the dt by dx. Right, now we have to replace this proportionality sign, and by replacing this sign with equality, we would have to introduce a constant of proportionality, which is K, and this K is basically the thermal conductivity, while this negative sign indicates that this temperature gradient is having a negative slope, have a decreasing slope, right? So has a decreasing slope. Now, because if this is, let me show you, if we have this surface T1 and this is T2, right, and it is at a higher temperature T1 and T2 is at a lower temperature, so you see that the heat transfer would be have a negative slope, and this is basically dt by dx, right, and over the distance between them is this dx, correct? Now we have actually reached towards this Fourier equation, which is for the use for the conduction, which is q of x is equal to, or the heat transfer rate in the x direction is equal to minus ka dt by dx. Now if we divide both sides by a, because a is constant, k is also constant, but if we divide this a, so it will give us the flux, heat transfer basically divided by a. Now this will give us the flux, and the units would definitely change to watt per square meter, right? So we will get an equation which will be minus k dt by dx, and this will be the equation of the flux. So this is called heat flux, and its unit is watt per square meter, while the heat transfer rate unit is watt. Now these are the two equations A and B, which is the representation of the Fourier's law of heat transfer for conduction in one direction, in x direction, which we have defined already. Now from this diagram you can see that this heat flux is basically parallel to this wall, or the area of the surface, normal surface, this isothermal surface. This q of x is normal, right? So the heat transfer rate is the flux is normal, because we are actually ignoring that particular, or we are dividing by this cross sectional area. So the direction of q of x is normal to the cross sectional area, and which actually implies that q of x with this double prime is basically heat flux, and that flux has a directional quantity, right? So it means that the heat transfer equation, or Fourier law of heat transfer, is a directional property, and whenever there is a directional property, so it can be written in this form, in a vector quantity, in a vector notation, and where we use this del operator with the t, which actually is used for the three-dimensional space, three-dimensional area. So if we conclude, so the heat flux, or the heat transfer per unit area, heat transfer rate per unit area, would be equal to minus k, this temperature gradient in the x direction, temperature gradient in the y direction, and temperature gradient in the k direction, or the z direction. And this k, j, i, n are the unit vectors basically defining the direction, and these are the scalar quantities, dt by dx, right? So this is the 3D equation of the Fourier's law in all the three directions, in the x direction, right, then in the y direction, and obviously in the z direction. But in that particular case, which we have already discussed over here, we have actually made this insulation over here, right? So there is no heat transfer in this direction, lateral direction. So that is why we have only selected this x direction, and in most of the cases here in this course we will be using for 1D, but however whenever there is for 2D or 3D, so we can also use this directional equation. So let's have a quick review that what is the heat transfer rate for conduction, or how the heat transfer rate for a conduction can be found, and that is basically using the Fourier's law. Fourier's law is basically the heat transfer rate equals to the minus k dt by dx times A. Right? Now where this K is the thermal conductivity and it is a material property, right? It is a material property and it depends upon the properties of the material, the structure, the composition of the material. The metals would have different thermal conductivity. In metals and alloys, different metals, different alloys would have different thermal conductivities. Similarly, different other materials would have different thermal conductivities. The more the value of the thermal conductivity, the more we would have the heat transfer rate, the higher the heat transfer rate. So metals usually have more thermal conductivity value than the insulators, right? So this is all about the Fourier's law of heat transfer, that how the Fourier law takes place. And if you have any kind of question, so please ask me. And thank you so very much. Part 2 for this lecture will be uploaded soon. Thank you for watching. Subscribe and hit the bell icon.